I will present Vitalis lemma. So let me describe to you what is a Vitali covering of a set of R. So this is a definition. And I will assume that I have a collection I alpha for alpha in some set F. These are intervals. This collection might be uncountable, just a collection. And I have a set E, which is a subset of R. And at this point, I'm not assuming that E it's measurable. So there is a subset of E. And I would say that this family of intervals is a Vitali covering of the set E if the following holds. So for any x in E and for any epsilon positive, I can find an interval. So there exists an interval I alpha in my collection of intervals such that, well, x has to belong to my interval I alpha, and the length of the interval I alpha must be strictly positive and smaller than this epsilon. So I'm representing by this symbol the length of the interval, and I want this length to be strictly positive and to be bounded by epsilon. So a family of intervals will be a Vitali covering of my set E. If for any x in E and for any epsilon, I can find one of these intervals which contains x and whose length is strictly positive and bounded by epsilon. So this is the definition. And now let me state the lemma which I want to prove. The following, well, let me take a set E which is contained in R. And let's assume that I have a Vitali covering. So let's assume that I alpha, it's a Vitali covering of E. And I will assume that, well, these sets I alpha are closed. This is not important. We can prove the same lemma without this assumption. But since I will be using Vitali coverings with closed sets, let's assume that all these intervals are closed. Then what I claim, and mind that I'm not assuming E to be measurable. E it's any subset. So what I claim is the following. Well, then I can find there exists a countable subcovering. So there exists a family ij for j greater or equal to 1. So this is a countable subset of this set. So let me give a name for that set. This is I. So this family ij belongs to I. What's important here is that these intervals are disjoint. So ij intersection ik, it's empty if j is different from k. So I can get a countable subfamily of this family of intervals which are disjoint 2 by 2 and for which, well, let me represent by lambda star the Lebesgue outer measure. I'm taking the outer measure because I'm not assuming E to be measurable. So I want the outer measure of E minus the countable union of these intervals ij. Well, what I claim is that I can find this subcovering in such a way that this outer measure it's equal to 0. So you see, when you have a compact set and you get, so this is this lemma, the closest lemma you might know from that one is that, well, take a compact set of R, take an open covering of this compact set, then you know that you can extract a finite family which still covers your compact set. Here, what we want, of course, when you take this finite covering, these open sets have non-empty intersection. It's clear that these sets do not have empty intersection. What we want here is to cover E as much as possible, but with intervals which are disjoint 2 by 2. So it's slightly different from that lemma. So we can't cover the old set, but what we can guarantee is that all points which are not covered by these intervals, well, their outer measure is equal to 0. So this is the lemma I want to prove in this lecture. So the proof of this lemma will be divided in a few steps. The first step is to reduce E to a bounded set. So what I claim is that I can assume E to be contained in an interval k plus 1. Okay, so why can I assume that E is contained? Well, I can always define Ek to be the set E intersection k plus 1. Suppose that in my covering, I can prove that lambda star of E minus this union. So what? Suppose that these sets Ij are all contained in k plus 1. Okay? So what I will prove is that if my set E is contained in the interval k plus 1, the open interval, then I will be able to find a family which is countable, which is a subfamily of my original Vitali covering, and in which all sets Ij, all closed intervals Ij, are contained in this interval k plus 1. And for these intervals, I will prove that the outer measure of E minus this union is 0. So assume that I can prove these results. Then I can prove the general result in a very simple way, define Ek. So we know that I can find, according to this lemma, a family which will now be indexed by k. So Ek minus the union from j larger or equal to 1 of I, let me represent these intervals by Ik, j, just to remember that these intervals will depend on this set Ik, for which this measure here, the outer measure of this set, it's equal to 0. Then, since for fixed k, these intervals are disjoint by 2 by 2, and since for fixed a, all these intervals are contained in k plus 1, it's clear that the family of Ekj for j larger or equal to 1 and k in Z, that this family, it's a family of a subfamily of my original family for which these intervals are all disjoint 2 by 2. So what I'm claiming is that Ejk intersection Ej prime k prime, that this intersection is empty if the pair Gk is different from the pair G prime k prime. Right? So this family is disjoint 2 by 2. And of course, E, if you take a point in E minus the union for k in Z and the union for j larger than 1 of I, k, g, j, well, of course, I removed all integers from this set. So this is contained in Z union, of course, because, well, maybe E contains an integer, and I'm removing this integer when I'm taking the intersection of E with this open interval. So maybe there are points which are integers. And then, well, this is clearly contained also in the union for k in Z, union j larger than 1 of ek minus the, I'm sorry, union of ek minus the union j larger or equal to 1 of I, k, j. Okay, so I claim that this is true. Indeed, if you take a point in E, which is not an integer, then it belongs to one of these sets ek, but it doesn't belong to this union, so it might belong to one of these ek, but not to this union. So this set is contained in that one. So the measure of the outer measure of this set, it's bounded by the outer measure of this set plus the outer measure of this set. The outer measure of Z is 0. The outer measure of this set is bounded by the sum in K of the outer measure of these sets, but the outer measure of these sets are equal to 0, and therefore the outer measure of that set is equal to 0. So this argument shows that in order to prove the lemma, it's enough to prove the lemma for a set E, which is contained in k plus 1. But in this proof, we will need to use only intervals which are contained in the interval k plus 1. So this is what I will prove next. And of course, I will take k equal to 0, so I'll assume that my set E is contained in the interval, the open interval 0, 1. So I'm assuming that I started with a set E. I took its intersection with 0, 1. So now I have a new set E prime, say, which is contained in 0, 1. And I have a Vitali covering of my set E, not E prime. And I'm assuming that these sets are closed. So my first observation is that this family, I alpha, it's a Vitali covering of my new set E prime, which is E intersection 0, 1. Okay, and this is clear because, well, take a point x in E prime. So x belongs to E. Since x belongs to E, and this family, it's a Vitali covering of my set E, so there exists, if I fix also an epsilon positive, there exists some I in my family. So let's remember that I'm calling I this family. So there exists alpha I in I, such that, well, x belongs to I alpha, and the length of the interval is bounded by, well, strictly positive and bounded by epsilon. And therefore, this family, it's clearly a Vitali covering of my set E prime. Okay? So this is a covering of E prime, and we can start by now considering that I have a Vitali covering of this set E prime, which is contained in E0, 1. Now I will do a modification. I will call EI bar, say all I alpha, such that, well, alpha is one of these sets, But what I require now is that these sets I alpha, which are closed interval, are all contained in 0, 1. Okay? And I claim that this new set, I bar, is a Vitali covering of my set E prime. Okay? So I'm removing from my original collection all intervals which are not contained in the interval 0, 1. And I'm claiming, well, that this new collection, which is smaller than the former one, well, it's still a Vitali covering. And the proof, it's very easy. Take epsilon x in E prime and take epsilon positive. Okay, since x belongs to E prime, it's a point in the interval 0, 1. Okay. So now, for that fixed epsilon, I know that there exists an interval in my original collection which contains x and which is as small as I want. So here's my point x. So if I take, if I call delta the minimum between epsilon, this distance, which is x, and this distance, which is 1 minus x, delta, it's strictly positive because epsilon is positive and x is between 0 and 1. And therefore, I know that there exists an interval I alpha in my collection I such that, well, x contains I alpha, x is contained in I alpha, and the interval I alpha is such that its length is strictly positive and bounded by delta. Well, but if x it's contained, so here is my interval, since x belongs to my interval I alpha, and the length of this interval is smaller than x and smaller than 1 minus x, it's clear that this interval is contained in 0, 1. So since I alpha it's smaller than delta, and I alpha and x contains and x belongs to I alpha, it follows from these two facts that I alpha is actually contained in the interval 0, 1. Right? And therefore, it belongs to I bar. So I alpha actually belongs to I bar, and his length, it's smaller than epsilon because delta is smaller than epsilon, and it's strictly positive. And this proves that this family, in which I'm removing all intervals which are not contained in 0, 1, is still a Vitali covering. So I can start my proof by assuming that the set E is contained in the interval 0, 1, and that all intervals of my Vitali covering are contained in the interval 0, 1. So this is the end of the second step of the proof, and now I will start the proof under these assumptions. So in the first two steps of the proof, I showed that it's enough to consider a set E contained in the interval 0, 1, and a Vitali covering, and that my Vitali covering of my set E has the following properties. Well, the intervals are contained in the open interval 0, 1, and since the beginning, I'm assuming that they are closed. So now I can prove, I can really start the proof of Vitalis' lemma, and I will construct these countable subcovering of the joint intervals which almost cover my set E. And the proof of this lemma will be now performed in two steps. So in my first step, in step 1, I will construct by induction a sequence of intervals I1, I2, and so on. They will be members of this family, and they will be disjoint 2 by 2, and these will be the intervals which will cover E. So remember that what we want to prove is that the outer measure of my set E minus the union of ij, it's equal to 0. So this is what we want to prove. We want to construct this countable subfamily which almost cover the set E. How shall we proceed? Well, if my set E is empty, there is nothing to prove, right? Just take any family, it's fine. So let's assume that E is not empty. Well, if E is not empty, let's consider, let me call alpha 1 the supremum over all lengths for, maybe alpha is not a good name, let me call that S1. S1, so it's the supremum over all possible lengths for alpha in F. And since E is non-empty, well, this supremum is strictly positive, right? Because, well, if E is not empty, I can find a point x in E. There exists an x. If there exists an x, well, there exists an interval I alpha such that x belongs to I alpha, and the length of I alpha is strictly positive, right? So this family is not empty, it has an element, this element has strictly a length strictly positive, so S1 is strictly positive. And also, well, and this is where I will use this fact, since all these intervals are contained in the interval 0, 1, well, the supremum over all lengths, it's bounded by 1. So S1 is strictly positive and less or equal than 1. And since this is a supremum, I can find, and this is the definition of my set I1, I can find a set I1 which belongs to this family, and such that, well, the length of I1 is almost equal to S1. So I will take the length of I1 to be larger than S1 over 2. I can find one which is almost S1, therefore I can find one which is whose length is larger than S1 over 2. So this is my first interval, and now I will proceed by induction constructing these family. So let me explain you how I define my set I2, and then I will consider the general case. Well, I will repeat exactly what I did in my first step. Let's consider the point E, the set E minus I1. Well, if this set is empty, then there is nothing to prove, right? I can complete my, or I can just consider here a finite family, and I'm done. Because, well, this is empty, so the outer measure is 0. Well, if it's not empty, then I can find the point x in E minus I1, and I can consider, let me define S2 exactly in the same way I defined S1. This will be the supremum over all the intervals I alpha, but now I will require that I alpha belongs to my family, as it was the case here, but I will also require I alpha to be disjoint from I1. So let me define S2 as the supremum over all lengths of intervals which belong to my class of intervals and which are disjoint to I1. by the same reasons as before, this supremum, it's bounded by 1. It's less or equal than 1. And I claim that it's strictly positive. And why is it strictly positive? Well, because I'm assuming that E minus I1 is non-empty. If E minus I1 is not empty, I can find a point X. Well, this point X does not belong to I1. So it has a distance. So here is my interval I1. So it has a distance. And if I take I alpha, so I know that there exists an interval I alpha which contains X and whose length is as small as I wish. So if I take the length of I alpha smaller than the distance from X to I1, so let me call dxI1 the distance from X to the interval I1. Well, if this length is smaller than that, this implies that I alpha is disjoint from I1. And therefore, this shows that this set is non-empty, so I can find one interval in my family which is disjoint from I1. This element has a strictly positive length, and which proves that this supremum is strictly positive. So, as in step 1, I can prove that S2 is strictly positive and bounded by 1. If it's strictly positive and bounded by 1, well, this means that I can find, so there exists an interval I2, whose length is almost S2. So I will require, as before, remember that in the first step I required I1 to have a length greater or equal than S1 over 2. So let's require the length of I2 to be greater or equal than S2 over 2. And I2 belongs to this set. So this means that I2 intersection I1, it's empty. Okay? So this is my step 2. In my second step, I constructed a second interval, which is disjoint from the first one, and whose length almost reach the maximal length. So let's continue. So assume that we constructed the set I1, I2 up to In minus 1. What are the properties of these sets? Well, they are written here. They are disjoint 2 by 2, and their length reach, well, it's bounded below by the maximal length divided by 2. So let's construct my set In. So this is my final step in my final argument in this first step, which consists in constructing this family of intervals. So I want to construct In. Again, I will proceed. I will consider, well, if E minus the union of Ij from j from 1 up to n minus 1, it's empty, well, there is nothing I need to do because I have already that the outer measure of this set, it's 0. So let's assume that it's not empty. If it's not empty, let me call Sn, as I did here, the supremum over all lengths of intervals I alpha which belong to my family I, and such that the intersection of I alpha with I1 union I n minus 1, it's equal to 0. It's empty. So let's consider that set. Sn, it's less or equal than 1 because all lengths, all intervals are contained in 0, 1, so they have length bounded by 1. And now I claim that, well, Sn is strictly positive. And I will just repeat the previous argument. Well, since this set is non-empty, I can find a point which belongs to this set. So this point x belongs to E and does not belong to these intervals. These intervals are closed. So there is a distance from x to these intervals. So here are the intervals. So there is a distance from, strictly positive distance from x to these intervals because these intervals are closed. So here I'm using the fact that the intervals are closed. And now I know that x, it's covered by one of these intervals, and I can impose the length to be as small as I wish. So I can take a length smaller than this distance. So there will be here an interval which covers this point and whose length is smaller than the distance. If the length is smaller than the distance, this means that this set, which I just constructed, is disjoint from the other ones. So this family, it's a non-empty family. Each of these intervals has a strictly positive length because it's a Vitali covering, and therefore this supremum is strictly positive. Since this supremum is strictly positive, I can find a set In which is disjoint from the first n-1 intervals, and such that his length is as close as I want from Sn. So I'll take the length to be larger or equal than Sn over 2. And this is how I construct by induction these intervals. So at the end, either I stop somewhere because, well, this set is empty, or I continue forever because, well, this set is never empty. So I can just iterate this argument to construct a countable family of intervals, which are disjoint 2 by 2, right? They are disjoint 2 by 2 by construction. And moreover, well, the length of each interval, it's bounded below by the maximal length divided by 2. So now I will erase the blackboard, and I will start from this family, and I will prove that this set is actually equal to 0 for the family I just constructed. So I wrote what we proved in this first step. What we did, we construct a countable family of intervals, I1, I2, and so on. They are disjoint 2 by 2. They belong to this family I. And they have the following property. If I define Sn as the supremum over all lengths of all intervals in my family, which are disjoint from the first n-1 ones, then this is Sn. This is the maximal length of these intervals, the supremum of these lengths. Well, the one I constructed has a length which is larger than Sn over 2. So I wish to prove that identity. I'll first make a very simple observation. Well, if I consider the total length of these intervals, these intervals are disjoint. This is a measurable set, so the outer measure coincides with the measure for measurable sets. So this is equal to, well, the lengths, the sum of the lengths. Okay. But each of these intervals are contained in 0, 1, so this union is contained in 0, 1, so it's bounded by 1. So this means that this sum is bounded by 1, and therefore, well, if I start the sum at large integer n, I can make it as small as I wish, because, well, the total sum is finite. So that I will use later on, the fact that this. So this means that if you, what I just said, that if I started my sum from n of ij, that this is converging to 0 as n increases to infinity. Okay? So this is an observation. Then, well, I have these intervals in. Let me define a new sequence of intervals kn. So how do I construct kn? Here is in. Right? In has a certain length. So what I will do, I will multiply this length by 2, and I will add on the left of the interval this interval, and I will repeat the same thing on the right side. So I'll take 2 times in. So this is 2 times the length of in. So I include an interval on the left endpoint of in of length 2in, and I do the same at the right endpoint, and this gives me an interval which I'm calling kn. Okay. So from in, I'm defining this new interval kn, and my claim is the following, is that if I take E minus the union of ij from j from 1 up to n, then this set, it's contained in the union from j larger than n of kj. Okay? So I claim that if you take this set, that this set is contained in this set. And this is what I'm going to prove. And once we prove that claim, it's easy to conclude by using this observation. So let's prove this claim. So in order to prove that claim, I have to take a point in this set and show that it belongs to that set. So let's take a point in X in E minus the union of ij. Well, now X, there exists an interval j, right? Since X does not belong to I1 up to In, I can find an interval j which belongs to my family I, okay, such that X belongs to j, and j has no intersection with I1 up to In minus 1. Okay, by the same reasons, I have a point X which doesn't belong to any of these intervals, so it has a distance with these intervals, so I can choose an element of my Vitali covering which is sufficiently small in length, which contains X and which is disjoint from all the previous intervals, all intervals I1, here In. Okay. Since I'm going up to In, I can find this interval j. And what does that mean? Well, that means that j belongs to this family, to the family of intervals in my collection I, which are disjoint. So this is up to n. So this means, so remember that Sn was the ones which are disjoint up to n minus 1. So this means that you're in this family with n instead of n minus 1, which means that j, the length of j, it's bounded by the supremum, which is Sn plus 1. Okay? So I know that j is bounded by Sn plus 1 because it belongs to this family with n in place of n plus 1. Fine. So I have this interval. I construct this interval. And what I claim is that this interval j has an intersection with some Im. It has to have an intersection with some Im for some m larger than n plus 1. Okay. Why is that so? Well, because assume that J has no intersection for all M between, well, I know that it has no intersection with the first N, so I assume that this is true for M between N and say N prime. Okay? Well, but since it has no intersection with the first N prime ones, it means that it belongs to this family, which means that since it belongs to this family, for the same reasons I claimed here that its length has to be smaller than Sn plus 1, this means that the length of J has to be smaller than Sn prime plus 1, right? If J has no intersection with the first N prime intervals, it means that it belongs to this class of sets up to N prime. So I have here N prime instead of N minus 1, which means that his length has to be bounded by Sn prime plus 1, which is what I wrote here. But you see, since these lengths are summable, this is what we have here, it means that the lengths are converging to 0. So not only the sum is converging, well, the sum is converging to 0, which means that also the lengths are converging to 0. But Sn plus 1, by construction, Sn prime plus 1, it's bounded by 2 times I n prime plus 1, right? We constructed the interval I n prime plus 1 in such a way that its length was almost equal to the supremum. So the supremum, it's bounded by 2 times the length of I n plus 1. And this length, it's converging to 0. Well, but J, it's strictly positive, right? Because when I constructed J, I constructed an interval in my Vitali covering, and his length was strictly positive. So here, we get a contradiction if J has no intersection, right? Because, well, if J has no intersection with the first n prime ones, his length is bounded by that. But since it's really positive and this is converging to 0, that can't be true for all n prime. So J has to have an intersection. There exists at least one M for which J has an intersection with IM. I hope you're convinced by this argument. So there exists M. There might be more than one. So let me take the first M for which J has no intersection. Okay, so let's take, so I'm assuming here that J has no intersection with, has an intersection with IM, and that J has no intersection with the first M minus 1. Okay, so M is the first integer larger than n for which J has an intersection with IM. Well, but what do we know? Since J has no intersection with I1 up to IM1 minus 1, it belongs to this class with n replaced by m, which means that his length is bounded by Sm. So the length of J, it's bounded by Sm. On the other hand, I know that Im was chosen in such a way that his length is larger or equal than Sm over 2. So Im, on the other hand, it's larger than 2Sm. Okay? Now, mind, we know that J has an intersection with Im, that its length is bounded by Sm, and that the length of Im is larger than 2Sm. So what I claim is that J is actually contained in Km. Why is that so? Well, here is, so now let me replace n by m, okay? I know that Im has an intersection with Jm. So let's write here Jm, J. So here's the set J, and Im has an intersection with J. I know that J, it's bounded by Sm, and that Sm, it's bounded by half of, I'm sorry, here I wrote 2, but actually it's divided by 2. So there was a mistake here. Im, it's not larger than 2 times Sm, but it's larger than Sm divided by 2. Okay? So J, it's bounded by Sm, and Sm, it's bounded by 2 times Im. Okay? So the total length of J, it's bounded by 2 times the total length of Im. So since J, the total length of J, it's bounded by 2 times the total length of Im, which I wrote here, and since it has an intersection, this interval has to be contained in the larger one, or at least, since it's on the right, it's contained from Im union this interval. And this proves, therefore, that J, it's contained in Kn, which is exactly what I wanted to show here, because since X belongs to J, and I just proved that J is contained in Km, this shows that X is contained in Km, and therefore X is contained in this union. So this proves my claim. So let me repeat if it was not clear. J, it's an element of this family, and therefore his length, it's bounded by Sm. Im was chosen in such a way that it almost attains the supremum, so the length of Im, it's bounded below by Sm divided by 2, and therefore Sm, it's bounded by 2 times Im. So I know that the length of J, it's less or equal than 2 times the length of Im. So now J, I know that J, the interval J, has an intersection with Im, so it's either on this side or maybe on that side. So let's assume that it's on the right side. So it has an intersection with Im, so this point here, which is the right-hand point of Im, has to belong to Im and to J. Now, the length of J, it's bounded by 2 times the length of Im. Well, in the worst case, J will be exactly, the intersection will be reduced to a point. The length of J is bounded by 2 times the length of Im, but this is exactly what I added to Im to form Km. So J, it's contained in Km. And if J is contained into Km and M is larger than N, this means that since X belongs to J, X belongs to Km, and therefore X belongs to that union, and this proves that this set is contained in that one because I took a point in this set and I proved that it's contained in this set. So now I will erase all I did to reach that conclusion, and I will complete the proof starting from here. Well, the conclusion is very simple. The outer measure of AE minus the union since this set is contained on that one, the outer measure of that set, it's contained in the outer measure. It's less or equal than the outer measure of this set. Right? Well, the outer measure of this union, actually here I wrote a sum, but it's a union because, well, these sets may, I'm not claiming that these sets have no intersection, so actually this is a union. Sorry for that. So this is a union. So the outer measure of this union, it's less or equal than the sum of the outer measures. Well, these are intervals. So the outer measure of this interval is just the length of this interval. And if you remember, the length of this interval, it's equal to 5 times the length of the interval ij. And by my observation, the sum of the lengths, it's converging to 0. So this expression, it's converging to 0 as n goes to infinity. Right? So this outer measure, it's converging to 0 as n goes to infinity. Well, but this set, it's clearly contained in that one. I'm taking out here many more points than in that one. So the outer measure of that set, it's less or equal than this one, which depends on n. But the outer measure of this set, it's converging to 0 as n goes to infinity. So the outer measure of this set has to be equal to 0. Right? The outer measure of this set is less or equal than the outer measure of this set, which is converging to 0. So the outer measure of this set is equal to 0, and this completes the proof of Vitalis' lemma. So if you're not happy, well, I'll complete this lecture with two simple remarks. The first one is the following. Well, if you're not happy with the fact that I assumed the intervals to be closed, let me mention that this is not needed. So the assumption that the intervals I alpha are closed is not needed. And let me show you why. So let's assume that I alpha, it's a Vitali covering, right? So let me call J alpha. So these are intervals. So let me call J alpha the closure of I alpha. So now J alpha is a family of closed intervals. So these are closed. What I claim is that it's a Vitali covering. Okay, because, well, why it's a Vitali covering? Take X. So there is a set E. Okay. We started with a set E, and with a Vitali covering of that set by intervals, which are not necessarily closed. Well, but now J, it's closed. Take X in E, and take epsilon positive. Then, since I alpha, it's a Vitali covering, I can find I alpha such that, well, X belongs to I alpha, and the length of I alpha is strictly positive and bounded by epsilon. Well, of course, X belongs to the closure, right? Because, well, the closure contains I alpha, so X belongs to J alpha, and the length of J alpha is the same. Okay? So it's clear that this new family, J alpha, now is a Vitali covering of my set E, and that all elements of this Vitali covering are closed. Now, by the lemma I proved, I know that I can find a countable covering such that the outer measure of E minus this covering is 0. Well, but it's clear that if you take the set E minus the union of Ik, okay, remember Jk was obtained from I just by taking the closure. So let me take Ik as the set which originated the interval Jk. Well, this set, it is contained, well, either it's a point in E minus Gk, or it's the union, so let's assume that Gk, it's a closed interval, so it's Ak, Bk. So this is the union of Ak bk for k larger than 1. Okay? Either if you're in this set and you are not one of the endpoints of gk, so if you belong here, you have to belong here. Now, so the outer measure of this set, it's bounded by the outer measure of this set plus the outer measure of that set. The outer measure of this set, well, this is a countable set, has, well, it's measurable, it has measure 0, and this one, by the Vitali lemma for closed interval, it's also equal to 0, and therefore you conclude. So this remarks shows that actually you don't need, in Vitali's lemma, to assume that the intervals are closed, though I will only use in the next lectures closed Vitali coverings. But anyway, this shows that you don't need that hypothesis in the lemma. And my last remark of this lecture is the following one. So assume that our set E, it's contained in an interval minus L, L. Okay, it's a bounded set. And assume that you have an Vitali covering. So this is a Vitali covering. Of E. Well, we proved that we can extract a countable family for which cover almost entirely my set E. So now, in the proof, we show that we can remove from these collections all intervals which are not contained in 0, 1. So here we can repeat the same proof and remove from this Vitali covering all intervals which are not contained in minus LL, keep that Vitali covering, repeat the proof in order to get this result, but now for intervals which are all contained in minus LL. That's fine. So now what I want to claim is that, well, if you give me an epsilon, then I can find a finite covering which almost covers. So I can get a covering up to epsilon, right? So what I claim, well, now I have a new statement, which is a corollary, if you want, of Vitali's lemma, which is the following. Assume that my set E is contained in minus LL. Then, given any epsilon positive, I can find a finite subfamily of intervals for which what remain out of this union, so the outer measure of E minus this finite union, it's bounded by epsilon. And this is clear because, well, this set here, it's contained, well, either you belong to E minus the entire union, or you belong to one of the last elements. Okay. Or so this set, it's contained in this set, union that set, right? Because if you belong to this set and you do not belong to this set, then you have to belong to one of these. But this tells you that the measure of that set, it's bounded by the measure of this set, or the outer measure of this set, which is 0, plus the outer measure of that set, and the outer measure of, so what I'm saying is that this set, it's contained in that one, and therefore the measure of this set, it's bounded by the sum for k larger than n of the outer measure of ik. Right, and this is, well, the sum for k larger than n of the length of these sets. And we have seen that as n goes to infinity, this length converges to 0. So we can choose n sufficiently large for that sum to be bounded by epsilon, and therefore for this measure to be bounded by epsilon. So what we obtain here, it's a corollary of Vitalis' lemma, which states that if my set E is bounded, then for any epsilon, I can find a finite covering. Keep in mind so that these sets are disjoint. So I can find a finite disjoint covering of my set E, such that the outer measure of E minus this finite union, it's bounded by epsilon. And this completes the lecture. So in the next lecture, I will use this result to show that any monotone function is differentiable almost everywhere.